Yeah, thank you very much, Ute, for the introduction, and thank you very much to the organizer for inviting me as well. I'm very excited to talk to you today about reinforcement learning for integer programming learning to cut. So first, I'd like to thank my collaborators, Shipra and Yuri, both at Columbia University. So in this workshop, we've been talking about machine learning for combinatorial optimization. So there are many ways of using machine learning techniques to try to help accelerate or solving combinatorial optimization problems. One method is to directly predict the solutions conditioned on the representation of the problems. So in this case, we have to think about the parameterization of the solutions as well as the architecture that can be tailored to the specific problems that we try to predict. Or we can take a more neutral approach that gets us closer to an algorithmic approach. That is, we can design a neural architecture to mimic algorithmic computations. So in this case, we're able to combine the flexibility of the representation learned by machine learning methods, as well as the inductive biases that come from an algorithmic, algorithmic thinking. But there's also a third approach, which is to directly combine machine learning with hard-coded algorithms. In this case, what we try to do is to use machine learning techniques to automate certain decision-making of algorithms. And in this case, we can replace some of the human design heuristics that's part of these popular algorithms. Prior work has already studied a lot on algorithms such as the branch and bound, also a lot of work on primal heuristics. And in this work, we're going to focus on cutting plane methods. And as you can see, all of these three approaches are part of a bigger spectrum of this entire array of approach that apply machine learning to combinatorial optimization problems. On the top, we have more like a pure machine learning-based predictions that allows us to benefit from the flexibility of machine learning representations. But on the bottom, we can combine machine learning with pure classic algorithms so that we can benefit from decades of research from hard-coded algorithms to solve combinatorial optimization problems as well. So why are we interested in cutting plane methods? Cutting plane methods are backbone of many of these very powerful modern commercial solvers. First thing that's very good about them is that they're agnostic to the underlying problems that we have. And it's also a very powerful approach. For example, we can have very efficient algorithms for solving hard problems such as TSP using cutting planes. One major challenge of considering cutting plane methods is that there's no very well-established principle for choosing cutting plane. That is, we don't have very good supervision or supervised learning signal in this case. It's not the case for example, in branch and bound, where typically people consider full storm branching as a golden rule or oracle for supervised learning. So we can directly apply supervised learning methods to try to learn ML model that does something similar to full storm branching. Or in the case of primal heuristics, typically we can first solve these problems and use the solutions directly as supervised learning signals. In the case of cutting plane, though, it's not clear what is a general purpose good approach to selecting cutting planes. Before diving into the specifics of cutting plane, I'd like to start with some background on integer programming. So integer programming is a very generic formulation for discrete optimization problems. So as you can see here, in general, we have a optimization problem with the decision variable x. We have c here as vector, which denotes the cost vector. So we try to minimize c transpose x. Under the constraints, ax is less than or equal to b, which gives us a set of linear constraints. And in addition, we have another integrality constraint that require x to be, all the components of x to be integer valued. But of course, in general, we could also just require part of the components of x to be integer valued. As you can see here, integer programming really encompasses a large array of problems that we deal with in discrete optimization. It can deal with problems on graph or planning problem or resource allocation, many of the popular combinatorial optimization problems as well. But in general, solving general integer programming problem is very challenging. It's mainly because of the discrete nature of the problem, because of this constraint that we have here that makes solving this problem much more difficult. So that if we try to do a continuous relaxation of this original problem and try to, for example, solve it with continuous approach, the final solution that we get can be arbitrarily bad. in the worst case. So in terms of cutting plane approach, the main idea is to, instead of solving the original integer programming problem, which is very challenging, let's solve the linear programming relaxation. So let's say we start with the original IP formulation, and we start with a LP relaxation. That is, we drop the integrality constraint on the solution X. And solving this linear programming problem is actually pretty easy. We can solve it very cheaply using, for example, simplex method. And after we get the solution, the solution should be X star here. And we try to check if X star, all of the components of X star are integer valued. If all of the components of X star are integer valued, then we already arrive at the optimal solution to the original IP problem, and then we're done. But usually it's not the case. And if X star has some non-integral components, usually we can come up with some sort of constraint in the form of E transpose X less than or equal to D. Then we're able to augment the original linear programming system by this new set of constraint. And we can add this new set of constraint to the LP, and we try to solve this new linear programming problem again. And we iterate this procedure until we either meet some termination criterion. For example, we terminate after 50 iterations, or we terminate until we find the optimal solution, until we find a solution where all of the components are integer valued. And in this case, all of these new constraints, E transpose X less than or equal to D, is called cutting plane or cuts. They're essentially the constraints that allows us to tighten the original linear programming formulation and provide us with increasingly tight LP relaxation to the original IP problem, so that we get closer and closer to the final solution. So as you can see here, the algorithm generates a sequence of linear programming optimal solution from X0 star all the way to XT star, where T is, for example, a fixed number of iteration. And we just hope that at the end of the day, XT star will be close to the optimal solution to the original IP problem. So just to recap what we have from just now, we start with this linear programming problem, and we check if X star belongs to the integer set. And if it is not the case, typically we're able to generate a set of cutting planes or set of constraints that we can add to the original system. Then we can just choose one of these constraints. For example, we can set here I to be 1 or 2 or 3. But one major question is, how do we generate these cuts? In this work, we mainly consider Gomery's cuts. So that's because Gomery's cutting planes are very general purpose. They can be directly calculated from the LP tableau. So that is, given the simplex method that solves the original LP relaxation as well as the optimal solution, we're able to directly compute the Gomery's cutting planes, these E1, E2, and E3. And it can be shown theoretically that this procedure can terminate with finite number of iterations, given some conditions. However, a downside is that the number of iterations or the number of cutting planes that we need to add to the system might be exponential in the size of the original problem. So this really depends on the sequence of cuts that we add to the system. If you're lucky, the entire algorithm may terminate very quickly within, say, 5 or 10 cuts. But if you're unlucky, the algorithm can get stuck for a very long time, adding a bunch of redundant cuts before arriving at the final solution. So it might be very costly to run such an algorithm. So the main motivation for this work is to ask the question, can we learn which cutting plane to add in order to minimize the total efforts of solving the original problem? So just to give a quick intuition about how cutting plane work, let us consider a 2D example. Here we have X and Y axis as these two axes of decision variables. And we have this dashed green line here that outlines the feasible set, which is basically being characterized by the constraint AX less than or equal to B. And here the yellow array, the yellow arrow will denotes the objective value. So in this case, let's say we're trying to maximize the objective. In this case, as we can see here, the integer optimal solution will be because these red dots here are the only integer that's in the feasible set. So that means that the only optimal solution that we can find will be these two red dots. Whereas if we relax the problem to the LP formulation, then the optimal solution is this rightmost blue dot. So let's say we add one cutting plane. The cutting plane would basically cut off the original LP optimal solution, and then we will arrive at this new optimal solution, which is here, which is this new blue dot. We can keep adding this cutting plane because the optimal solution that we get from these LP relaxations are not yet integer valued. So we'll keep doing this until eventually we arrive at a LP solution, which is also integer valued. So as you can see here, by adding this sequence of cutting planes, we're able to reduce the volumes of this feasible set, and which get us increasingly close to the optimal solution to the original IP problem. The question is, how many cutting planes or how many iterations does it take for the algorithm to terminate? It turned out that if we add these cutting planes randomly, because in this case, at each iteration, we have a bunch of cutting planes to add. If we just randomly choose one cutting plane to add in each iteration, then in expectation, it's going to take 2n, where n is the distance between the initial LP solution to the origin, 2n iterations to terminate the entire algorithm. Whereas if we add this cutting plane in an optimal way, in a careful way, then we can terminate the entire algorithm in just n iterations. So as you can see here, their difference is not really that large. It's like just a difference of a linear factor. But in practice, this can make a very big difference. One more thing to notice is that selecting cutting plane is also not a one-shot decision-making problem. So let's say we start with the original LP relaxation, and we have a bunch of cutting planes to add to the system. Then we add, say, cutting plane number 1 to the original LP system, and we solve the new problem, and we see that the solution is still not yet optimal. It's still not yet integer valued, so we have not yet arrived at the optimal solution yet. So we have this new set of constraint E4 to E6 that we can add to the LP system. Then we add, say, cutting plane number 6 to the system again, and eventually arrive at the optimal solution X star. So as you can see here, what we can observe that the final solution X star depends on the sequence of cutting plane. In this case, it depends on the cutting plane number 1 and cutting plane number 6. So in general, this cutting plane selection problem is really not a one-shot decision-making problem. It requires reasoning about making a sequence of decisions over time. So what is the learning framework that we should use to tackle a problem like this? We argue that the answer should be using reinforcement learning. So just a quick background on reinforcement learning. In reinforcement learning, we have to specify a state space for the problem, also an action space, and a reward function, which an immediate reward function which results from taking action at state xt. And then the state of the system will transition to a next state xt plus 1. Also, we need to define a policy, which is a mapping from the state space to a distribution over action space. This policy is literally the recipe according to which the agent will act against the system. In this case, we can generate a stream of experience by allowing the agent to interact with the environment. And we try to optimize with a discounted objective function. In this case, as you can see here, we have gamma to the power of t, where gamma is the discount factor between 0 and 1, and RT here is the immediate reward. And we sum them up over time and take an expectation over the randomness in the policy and also in the environment. This will be the objective value that we set for the policy pi, and we try to maximize it. So to make it more concrete, let's consider probably a more popular example where let's say we have a robot agent that try to play video games. And the state here is that, for example, let's say we try to play this video game called Pawn. And in this case, I guess many of us have played some variants of this game before. So basically, in this case, we try to move the paddle around so that we can get the ball to be behind our opponents. So the state of the system can be considered as a screenshot of the image of the game. And given the screenshot of the image of the game, the robot will try to take an action. So the action will be basically moving this paddle upward or downward. After moving the paddle, we will transition to a next state, which will be the next screenshot of the game. But at the same time, we will get immediate reward. So this immediate reward will indicate whether the agent is scoring anything or not. So as you can see in this case, by maximizing the cumulative reward that the agent collect over time, we're basically asking the agent to try to win the game. If, for example, if once we can get the ball behind our opponent, we get a reward of +1, and otherwise we get a reward of 0. This means that we try to get the agent to score the reward of 1, which means to win the game. And because of the discount factor that we have here, which is in general between 0 and 1, we basically try to get the agent to win the game as quickly as possible. So by setting up this objective and by allowing the agent to optimize this objective with respect to the policy pi that it uses to react against the environment, we're able to train an agent that play the game very well. So the trick here is to try to formulate a cutting plane selection problem as a RL problem. So we have to define all the components of the decision process. So recall that we have this decision diagram. Let's say we still have an agent, and now the state is, instead of a screenshot of the game images, it will become the set of linear inequalities that we already have in our system from the LP relaxation, as well as the set of cutting planes that we can add to the original system. And the action, by observing this state, the agent will think about it and then react with one cutting plane to be added to the system. And then what the environment does, it will actually add the new cutting plane to the system and then move forward. And then we can iterate forward. But there's one missing component, which is the reward function. So we can, for example, define the reward to be -1 at each iteration. So that means before the algorithm terminates, we always receive a reward of -1. And because, as you can see here, then the expected value of the objective will be taking this form, where capital T here will be the number of iterations it takes to terminate the algorithm. So by setting a reward function like this, because the agent keeps collecting a negative reward of -1 at each time step, it will try to minimize the horizon, will try to get to the optimal solution as quickly as possible with fewer number of cutting planes as possible. But of course, there are issues with this naive reward. That is, it's not very informative. Basically, the agent receives a reward of -1 at each time step. It does not really know whether it does a better job at picking a better cutting plane or not. But recall that at each iteration T, we have a new LP relaxation, and we have a new optimal solution XT star. And this problem is basically allowing us to, this cutting plane method allows us to generate a sequence of integer programming of solution to these LP relaxations, and eventually we try to have this XT star to be close to the optimal solution. And we can define something called the integrality gap closure. What it measures essentially is distance between the LP solution and the initial LP solution. And as you can see here, we also scale it with the objective value. We can see here, like as we increase T, this integrality gap closure would increase over time, and it's upper bounded by the difference between the IP solution's objective and the initial LP's objective. So we can basically define the reward as the immediate integrality gap closure that we achieve by having one more cutting plane. And here the intuition is that we try to get the gap closure to increase as much as possible. So to make it more concrete, we can see here x-axis is the number of iterations and the y-axis is the gap closure that we have. And in this case, if we have two sequences of cutting planes added to the system, we have these blue curve and red curve. And we would try to add cutting planes such that we can maximize the gap closure as quickly as possible, so that we can use this the intermediate gap as a reward function, so that when the agent optimizes this objective, it would try to close the gap as quickly as possible. Of course, there's some also some other detailed work we have to do. First, we need to parameterize the policy. In this case, for example, when we play video games, we can just have a convolutional neural network that maps from the images to the two decisions up and down. But in this case, we have to try to come up with the architecture that map from the linear programming representation to the set of cutting planes that we can add to the system. One property that we want to have from the architecture is that the architecture should be invariant to the ordering of these linear constraints. I'll just quickly glimpse through the architecture that we use. Basically, we use a attention style architecture to.
You have 5 minutes left. It's still enough.
Yeah, thank you. Yeah, I will try to just skip through this part because I think this architecture that we use is fairly simple, and it's basically using an attention-based mechanism to calculate the score, and eventually we're able to calculate the probability of choosing a particular cutting plane using these scores. And finally, we still need to find an algorithm that optimizes the policy. There are already many off-the-shelf algorithms that can optimize for a reinforcement learning problem, Q-learning, policy gradient, or evolutionary strategies. In this work, we use evolutionary strategies. Its main advantage is that there is no need for backpropagation, which is a huge advantage in this case because the state space and action space are not very regular, and it can cause some challenge for batching the data set when you try to do backpropagation efficiently. And also the algorithm is very easy to be made parallel, and it also works pretty well in practice. So finally, let's just take a quick look at some of the experiment results. We test on a set of problems, and we always generate training instances and train our RL agents on these training instances and present the testing results. We also compare with a few commonly used human design heuristics. So the first question we want to ask is, can RL minimize the number of cutting planes? So as you can see here, as pointed out by this blue arrow here, the RL agent is indeed able to achieve the optimal solution with a fewer number of cutting planes compared to the other human design baselines. And then are we able to, for example, fix a budget on number of cutting planes? Can we maximize the integrality gap closure? So in this case, as pointed out by this blue arrow here, we could also see that the RL agent achieves a larger gap closure compared to the other human design heuristics. And finally, a probably more exciting application is that we can directly combine a cutting plane with a branch and bound algorithm. So the branch and bound is basically a exhaustive search algorithm that carefully partitions the search space, but at the same time it uses these LP relaxations to bound the values of the search tree. By adding cutting planes to branch and bound tree, we're able to tighten the LP relaxations, which will lead to better bound in the downstream algorithm of the branch and bound. So the way we measure the progress in the branch and bound tree is also using something like IGC, but please refer to our paper for more details about this. What we do is that we train a cutting plane agent directly on by maximizing this cutting plane objective and without any knowledge about the downstream application, and we directly test it with branch and bound. We can see that when we try to measure this IGC in branch and bound, the RL learned cutting plane can also lead to a better performance gains compared to other human design heuristics. And if you try to measure the number of nodes in the branch and bound tree it takes to completely solve the problem, we could also see, as pointed out by this blue curve here, the learned RL agent is also able to do a much better job compared to other human design heuristics. So just to summarize what we have so far, we formulate the cutting plane selection as the RL problem, and we can then train RL agents that outperform human design heuristics. But there are also some limitations for this work, which is the problems that we test on are relatively small scale. And also we constrain the agent to add only one cutting plane at a time. And for future work, we could also consider RL for other IP algorithmic components, such as branch and bound. And I'm sure that there are already some work that's going in this direction. And finally, thank you very much for your attention, and please feel free to check out a paper for more detail. Thank you.